Hello, it's Keith here, and this is lesson 12 of the Photon series of my Z80 programming tutorials. Well, what's the Photon series? Well, we're making this little game here, which I've just opened a silly menu on. Now, this is a simple Tron game, but basically it's a tutorial, as well as making a game, on how to plot pixels to a screen and how to read them from a screen. Now, we're using 256 color mode here, but actually I'm only using 5 colors because that's what the game was designed to use. So a bit excessive there, but it's still a practical example on how to plot and read pixels from a screen like this. Also, we're now using the Kempson joystick. We'd used the cursor keys in the past, or QAOP, but now we're using the Kempson joystick, and you can see I'm playing it fine here. Okay, well, that's what we're going to be looking at. Let's go over to the code and let's take a look. Now, we've covered the multi-platform code in other lessons, so we're just going to go over this platform-specific bit here, and we're going to go over some parts of it relatively quickly if they've been covered in other tutorials like the YQuest series, because a lot of the code here was copied from YQuest. Okay, well, the first thing we're doing here is we're defining some macros here. We're going to need to use the special opcodes that the Spectrum Next supports that are not normal Z80 opcodes, but the assembler I'm using doesn't support them. But no problem, we can just create some macros to do that, and that's what we're doing here. Actually, I've got those definitions twice here. Why has that happened? Let's delete one of them. Don't know quite how that happened. Anyway, we've got the color definitions here. The reason these are here is some of the systems don't have enough colors. We would want 4 colors in the background color. Some only have 3, or some may even only have 1. So we've got some definitions here, but here we've just got a straight mapping to the true numbers. Then we're defining some memory for the game's variables. In this system we're using memory address 7000. This is for systems where the program code is in ROM and we're using RAM for the game variables. We're defining the screen size here, 256 by 192. We're defining a variable here which sets some of the scales for the title screen and things. The title screen's all vectors. And then here is the start of our code. So we're setting up the palette here. We've done that before various times. And we're disabling the transparent color here. I was having a very silly problem where the magenta wasn't working, and the reason is one color was being defined as transparent and that color was magenta, so it was showing through to gray, and it got me very confused, but I figured it out in the end. So there we go. So we need to make sure if we're using magenta we turn the transparent color to something else. So that's what I've done there. Here we're turning on layer 2, which is the 256 color mode. We're going to have to discuss that some more later. And we're not enabling 14 megahertz here because this game's too fast as it is. Okay, here we're just blanking the user memory just to start the game off with zeros there. Then we're showing the main menu and waiting for fire. The main game loop is here. Now, what we're doing here is we're updating the tick. Now, if I just start the game a second time here, and we just discuss one of the game's features, if we just wait here. Now, if I press the fire button, I actually move faster, and this is so that I can try and catch up with the enemy if the enemy's ahead of me. Now, this is known as boost mode, and what this is this is something where basically we're only processing the player every other tick if boost mode is off, and we're processing the player every tick if boost mode is on. So that's what we're doing. Now, unfortunately, the updating of the counter in the corner, these are vector fonts, so a little bit slow. So we have to change the delay depending on if boost mode is on or off. You can see that happening there. Then we're reading in the controls here. We'll see that in a moment. We're using the Kempson here, the Kempson joystick. So we're basically checking if the keys are down. If no keys are down, we're clearing the key timeout. If any keys are down, then we're storing them. The reason we're doing the key timeout clearing if the key is released is because if we are changing direction, we don't want to keep changing direction while the player is holding a direction, because they would end up crashing into themselves. If I just start the game here, if I press left here, I only move left once until I release and press again. If I kept turning, if I held it down, I'd end up spiraling around into myself, which wouldn't be very good. I'd have a bad day then. So that's why we're doing that. After that delay loop, we start the routine here, and first we're checking if the key timeout is 0. If it's not 0, then we're going to skip over the key press processing here. Now, key press processing works like this. We're loading the current player direction pointer into HL and the current player acceleration pointer into IX. If left or right are pressed, we're decreasing or increasing the player direction using HL. Now, we then run set player direction, which will copy the new accelerations for the X and Y acceleration into IX here, and that's how we're turning around. So these are handling the direction turns. If a turn occurs, we're setting the key timeout so that the keys have to be released before the next turn. Now, the fire works differently, of course. If fire is pressed, we're checking if boost power is 0 or not, and if it's not, Then we are setting boost to 0. We set boost to 1, I should have said that earlier. We set boost to 1 here. If it's 1, then boost is off. If it's 0, boost is on. The actual decreasing of boost power and other things is all handled by CPU player. That's handling all of the CPU drawing, checking if the player's dead. All the stuff of the CPU player, if the CPU is dead and that kind of thing, is being done by handle CPU. No surprises there. We've got wait for fire here. This has been done before, but we've got a slightly different joystick routine. We're reading a Kempson joystick this time. Very easy to read a Kempson joystick. We just read in from port 31 and we get left, right, up, down and fire in the bottom 5 bits here. And that's what we're doing there. We're just ordering in these bits here to clear all of the unused ones so everything's nice and consistent for our code. We've got a command PSET HLDE, which uses a 16-bit X and Y coordinate, but we've got our more simple one, which just uses an 8-bit coordinate here, and this is the main one. Now, it's kind of very easy to set a pixel on the Spectrum Next in 256 color mode. 256 colors means 1 byte is 1 pixel. So all we're doing is we're calculating the memory address of the pixel we want to see, and we are setting it with D here, or we're reading it for our point command here. Now, BC is a 8-bit coordinate, so 0 to 255 or 0 to 192, so those both fit within an 8-bit coordinate. That's how we're doing it. And it's this get screen pos, which is converting an X and Y coordinate in BC into a memory address HL, and it's also paging in the correct bank of the screen. If you think about it, our screen is going to be a total of 48 kilobytes of memory, and the way we address it is we use the bottom quarter from 0 to 3FFF of this addressable memory range, which is usually ROM, and we're going to page in the VRAM into that area. Now, for writing, in the past we've done this, and what we do is we have it so that when we write to that area, we write to VRAM, but when we read from that area, we still read from ROM, which allows the firmware to keep working. We need to do something different this time, because that point command would be reading in bytes of the firmware, and it would not work, so we'd keep dying. So our get screen pos function here is calculating the correct third of the screen. It did this before, the old version we used, and it's sending that to port 123B in the top 2 bits here, and that will page in the correct bank for writing. That will work just fine, and it's also turning the screen on here and enabling the writing here, and that will be fine for our PSET command, but that's not good enough for our point command. This is where things get rather annoying for me. Apparently Core 3, the latest firmware of the Spectrum Next, supports a read bit. This bit here would be enabling read and disabling that ROM. The emulator I'm using doesn't use Core 3. I'm not particularly keen to bother updating my emulator because, to be honest, I find it quite annoying that they're still changing the firmware. The whole reason I program these old computers is because things don't change anymore, because the documentation's all complete and I can work reliably and know my code isn't going to change, and the Spectrum Next doesn't do that because they keep changing the firmware. So we're going to work around it. We're going to use the alternate method, so this is going to be more compatible with the old firmwares. What we're going to do is we're going to use next registers 50 and 51. These are part of the memory mapping unit. These are basically page flipping parts of the Z80 range to the Spectrum Next's extended memory. The extended memory works in 8 kilobyte chunks, so to set the bottom range 0 to 3FFF, we're having to use 2 of them. We have to shift the bits from here, which they were in for this, and we have to shift them to here so that they are a multiple of 8. Then we add 16, because 16 is the first bank of the layer 2 VRAM, and then we send this to next register 50, which will page in the first part of the range, and then we increment the bank and we send it to 51, which will do the second part of the range, and that will page in our VRAM into this area for reading, and we can now read with that point command. If we don't do that, we will keep dying because it will be reading parts of the ROM and thinking we've hit some kind of color. So that's what we're doing there. Here's the my palette routine. This is just the colors. And we've got a CLS here. This is exactly the same as before. We're just paging in the 3 parts of the VRAM and writing all the bytes to 0. And that's really all there is to it. The only tricky thing about this is that paging of the VRAM, and that's all it takes really. The rest of the code is very easy because of that 1 byte per pixel. Spectrum Next does have a nice screen. It's very good, the 250 color screen. It's just a shame they keep changing the firmware. Anyway, There we go, that's Photon ported to the Spectrum Next. As always, you can go to my website, you can download the source code for what you've seen today and you can compile it yourself. So hopefully that will be useful to you if you're programming the Spectrum Next. Anyway, we'll be coming back to all of this later. I'll be doing some more Spectrum Next programming later on with my next programming project, hopefully. So if you've liked what you've seen today, please like and subscribe, because if you like the videos, YouTube recommends them to other people and that really helps me out. And if you subscribe, you'll see all of the other content that I've got coming, which will hopefully interest you as well. Anyway, thanks for watching today. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.